Inside something smaller than a stick of gum, there are billions of tiny structures working together at speeds that feel almost unreal. Every time a program opens, a game loads, or dozens of browser tabs stay alive without crashing, it all comes down to one thing quietly doing its job: RAM. Not some abstract concept, not just a spec number printed on a box, but a physical object packed with microscopic architecture so dense that understanding how it's made almost feels impossible at first glance. The surprising part is that none of this starts in a high-tech looking environment. It begins with something incredibly ordinary: sand. Not the kind from a beach, but silicon-rich material that gets refined again and again until it reaches an almost unimaginable level of purity. At that point, it stops being just a material and starts becoming the foundation of modern computing. That purified silicon is melted down at extremely high temperatures, forming a glowing liquid that gets carefully shaped into a single crystal structure. This is important because any irregularity at this stage would ripple through everything built on top of it. From that molten state, a cylindrical ingot is slowly pulled out, forming one continuous crystal. It's not rushed. Precision matters more than speed here. Once cooled, that solid cylinder gets sliced into thin discs known as wafers. Each one is polished until the surface is nearly flawless, so smooth that even microscopic defects could cause problems later. At this stage, the wafer doesn't look like much, just a reflective disc. But this is where billions of memory cells will eventually exist. Now comes the process that transforms this blank surface into something incredibly complex: photolithography. This is where things start to get interesting. Imagine projecting patterns onto the wafer using light, except the patterns aren't simple shapes. They're incredibly detailed circuit designs, layered over and over again. A light-sensitive material is applied to the wafer. An ultraviolet light shines through a mask, imprinting a specific pattern. Wherever the light hits, the material changes, allowing certain areas to be etched away. This isn't done once, it's repeated dozens of times. Each layer adds something new: pathways, structures, or components that will eventually become part of a functioning memory cell. And these patterns are built at a scale so small that thousands of them could fit across the width of a human hair. At the heart of all of this are the two components that define DRAM: transistors and capacitors. Each memory cell consists of one transistor and one capacitor. That's it. Simple in theory, but incredibly complex in execution. The transistor acts like a gatekeeper, controlling access to the capacitor. The capacitor, on the other hand, holds an electrical charge. If there's a charge, that represents a 1. If there isn't, that's a 0. That tiny difference is what everything depends on. But there's a catch. Unlike some other forms of memory, DRAM doesn't hold on to that charge forever. It leaks, slowly but constantly. That means every single cell needs to be refreshed over and over again, thousands of times per second, just to maintain its state. So while billions of these cells exist on a chip, they're not static. They're constantly being read, rewritten, and stabilized in the background. Building these components requires multiple specialized processes. Ion implantation introduces specific impurities into the silicon to change how it behaves electrically. Oxidation creates insulating layers. Deposition adds thin films of material, and etching removes unwanted sections with extreme precision. Each step builds on the previous one. There's no room for error. A mistake at one layer could render an entire chip useless. Once the basic structures are formed, the next challenge is connecting everything together. This is where interconnect layers come in. Metal pathways, usually made from copper or aluminum, are added on top of the silicon structures. These act like roads, allowing signals to travel between billions of memory cells. Without them, the cells would exist in isolation, unable to communicate or function as part of a system. These connections are arranged in grids, rows, and columns that form what's known as memory arrays. This organization allows the system to quickly locate and access specific bits of data. Instead of searching randomly, it knows exactly where to go. Even with all this precision, not every chip turns out perfect. That's why testing begins before the wafer is even cut. Specialized equipment probes each individual section, checking for defects or inconsistencies. If a problem is detected, that portion is marked. Later on, those faulty sections won't be used. Once testing is complete, the wafer moves on to dicing. This is where it's cut into individual chips, known as dies. Each die represents a fully formed memory chip, or at least one that passed initial testing. These tiny pieces are then packaged. But packaging isn't just about protection, it's about connectivity. Each chip needs a way to interface with the outside world. That means attaching it to a substrate and connecting it through bonding wires or tiny solder bumps. These connections allow electrical signals to move in and out of the chip efficiently. Now, instead of a fragile silicon piece, there's a durable component ready to be assembled into something larger. That's where the RAM module starts to take shape. Multiple memory chips are placed onto a printed circuit board, or PCB. This board isn't random. It's carefully designed to ensure signals travel efficiently between the chips and the system they'll eventually connect to. Alongside the memory chips, there's also a small but important component known as the SPD chip. This stores configuration data, information that helps the system understand how to communicate with the RAM properly. At this point, the module starts to look familiar. It resembles the RAM sticks seen inside computers. But it's not finished yet. Every module goes through another round of testing. This time it's about performance. How fast can it operate? How stable is it under load? How much power does it consume? Not every module performs the same, even if they were made in the same batch. That's why binning happens. Modules are sorted based on their capabilities. Some are designated for higher speeds, while others are categorized for more standard performance levels. This ensures consistency for end users. For higher-end modules, heat spreaders are often added. These aren't just for appearance. They help dissipate heat, keeping the chips within safe operating temperatures during intensive tasks. Finally, branding and labeling are applied. At this stage, what started as raw silicon has become a finished RAM module, ready to be installed into a system. And once it's installed, all of that complexity disappears behind a simple function, making everything faster. Opening applications, switching between tasks, running demanding software. None of it would feel the same without this constant, invisible support. What makes it even more fascinating is that all of this happens continuously. Every time a device is powered on, billions of memory cells begin their cycle of charging, discharging, and refreshing, maintaining data in real time. There's no pause, no downtime, just a constant flow of information being stored and accessed in fractions of a second. And all of it depends on processes that operate at a scale so small that it's almost impossible to visualize without specialized tools. From refined silicon to layered circuits, from individual cells to fully assembled modules, the journey of a RAM stick is less about a single breakthrough and more about precision at every step. Because when billions of components need to work together flawlessly, even the smallest detail matters. By the time a finished RAM stick clicks into place on a motherboard, the journey behind it is already complete. But the real work is just beginning. Because what sits there quietly isn't just storage. It's a constantly active system where billions of tiny memory cells are switching states, holding and releasing electrical charge in perfect rhythm. Every click, every command, every background process depends on this behavior happening flawlessly and almost instantly. Each memory cell, built from that single transistor and capacitor pair, operates as part of a much larger grid. Rows and columns stretch across the chip, forming an organized structure that allows data to be accessed with precision. When the system needs information, it doesn't search randomly. It targets exact locations, activating specific rows and reading values across columns in a fraction of a second. That speed is what makes modern computing feel smooth. But underneath that smoothness, there's constant maintenance happening. Since those capacitors naturally lose their charge, the system has to refresh them again and again. This isn't optional, it's essential. Without refreshing, the stored data would simply fade away. So while it might seem like RAM is just sitting there holding data, it's actually in a continuous cycle of activity, reading, writing, refreshing, over and over, thousands of times per second. And this is where the earlier manufacturing precision really proves its value. Because when dealing with billions of cells, even a tiny inconsistency could cause instability. That's why the fabrication process is so controlled. From the way silicon is purified to how each microscopic layer is added, everything is designed to minimize errors and maximize reliability. Even the arrangement of interconnect layers plays a role here. Those metal pathways don't just connect components, they determine how efficiently signals travel. Shorter paths, cleaner layouts, and better materials all contribute to faster communication between cells. And faster communication means quicker access to data. Inside a working system, this translates into real-world performance. Applications open without delay, multitasking feels seamless, and large files can be handled without everything slowing down. It's easy to take that responsiveness for granted, but it all traces back to how effectively those memory cells are built and organized. The testing and binning stages also continue to matter long after manufacturing is complete. If this breakdown gave a clearer view into how RAM is actually made and why it performs the way it does, consider supporting the channel. Subscribing helps bring more deep dive factory walkthroughs and tech explanations like this.